How much electrical force does the proton exert on the electron in a hydrogen atom when the distance between them is 5.3 times 10 to the power of minus 11 meters? Okay, so this is going to come as no surprise, but in order to solve this problem, we have to employ Coulombs Law. So Coulombs Law tells us that the electrical force between two charged bodies is equal to the Coulomb constant, K, times the charge on one object, times the charge on the other object, divided by the distance between them squared. So we know the value of K, it's a constant. It's approximately 9 times 10 to the power of 9 Newton meters squared per Coulomb squared. We know in this case the elementary charge, so that'll be the charge on the electron as well as the proton. So the elementary charge, often quoted as little q, is 1.602 times 10 to the power of minus 19 coulombs. Again, that's a constant. So both of these numbers should be in some kind of formula sheet that you'll be provided for test situations, or maybe you can write them down yourself. And then we're also given by the problem that the distance between the two charges, so between the electron and the proton, is 5.3 times 10 to the power of minus 11 meters. So given all this information, we can actually solve for the electrical force acting between the proton and the electron. So K is 9 times 10 to the power of 9 Newton meters squared per Coulomb squared. Q1, let's say that that's the charge on the electron. That's going to be negative 1.602 times 10 to the power of minus 19 coulombs. Let's say Q2 is the charge on the proton. That'll be positive 1.602 times 10 to the power of minus 19 coulombs. Now the distance between them is 5.3 times 10 to the power of minus 11 meters. Maybe I'll grab this and move it down for you, just to make everything a little clearer. Slide that down here. And this will be squared. Make sure you don't forget that that is squared. So now, quick check on the units. I like to write all the units so that I can make sure that we end up with the final units that we expect. So we have Coulomb squared in the denominator here. Those will cancel with this Coulomb and this Coulomb. So these two Coulombs multiplied together give us a Coulomb squared in the numerator, which cancels with the Coulomb squared in the denominator. Then this meter squared cancels with this meter, which is also being squared. I'm not going to erase the two because we're still going to need to apply that square to this value. Okay, so now if we plug this into our calculator, 9 times 10 to the 9 times negative 1.602 times 10 to the minus 19 times positive 1.602 times 10 to the minus 19 divided by 5.3 times 10 to the power of minus 11 squared is going to give us negative 8.20 times 10 to the power of minus 8 newtons. That's what we expect. We ended up with units of newtons left over here, and those are units of force. Now this negative just indicates that the force is attractive. In this case, we can just quote the magnitude of the force in newtons. So the answer of 8.20 times 10 to the power of minus 8 newtons is acceptable.